Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of my houseboat again. It's a beautiful day. It's near the end of August. Okay, this is part 2 of the MSPC training course. I want to talk about clock generation. I talk about coherent sampling all the time. And coherent sampling is a big deal. I mean, if you go to YouTube and search for coherent sampling, you'll find like 3 or 4 of my videos. Nobody else talks about coherent sampling. Everybody else is a fucking idiot. Coherent sampling is super important. And without coherent sampling, the FFT is an approximation. That's what the people at Tektronix said. It's just a button on a scope. But with coherent sampling, you can resolve every picovolt of energy from a waveform or from any other thing. If you do modal analysis like my buddy Bruce Polo at Genred, you could look at vibrations that are too small to be noticed by anything. So it's really cool. Coherent sampling is wonderful. Now, in order to do it, you need a proper clock generator. And so on the Nextest Lightning, we had a clock generation scheme that was built by my buddy David Reynolds and his friend Jim St. Jean, and they did this up in New Hampshire. To perform coherent sampling, the Maverick clock generation system was upgraded. Lightning, the mixed signal tester, Lightning's clock generator lives in the MSPC and provides the master clock to the APG, that's the algorithmic pattern generator board in the Maverick, in the Lightning, which in turn provides the clocks to the individual digital pins. The clock generator also provides the clocks to the instruments, such as the AWI, the ACI, and the modulator. So here's a little block diagram which shows the MSPC clock. It's a 200 megahertz oscillator. It goes to a system clock PLL. Back then we used PLLs, phase lock loops. And I used phase lock loops back in the Navy on the big transmitters down in Australia. So our transmitters, every machine got a system clock. I think it was a 10 megahertz clock, and then we used PLL to get the frequencies we needed. So PLL generates any frequency you want, or you can just divide by 2 and get 100 megahertz. The APG had a 100 megahertz oscillator and what they call the APG PLL. So generally, the digital all use the 100 megahertz oscillator for their clocks. And that goes down to go to the slave controller and to the digital pins. The slave site controller in a Maverick, it has 64 pins. There's one APG board and one 100 megahertz oscillator. But if you go to the ST, which has 2 64-pin slices, one of the pin slices is in charge. So it runs the 100 megahertz oscillator, and then that is routed to the other 64-pin slice. So those other 64 pins run synchronously with the first 64, and so everything's, you know, calibrated to work that way, so that everything is running off the same clock. That's really, really important. With the SST, 256 pins, so that's 4 slices of 64 pins. So one APG has a 100 megahertz clock that runs all 256 pins are off the same 100 megahertz clock. The other APG clocks don't get used. And in the GT, that's 512 pins, so that's 8 slices, 8 64-pin slices. One guy is in charge, and everybody else is a slave to that, using the clock from the one master. But in the MSPC, we can use a 200 megahertz oscillator, go through the divide by 2 to get 100 megahertz, or we can go through the system clock PLL. And that gives us our system clock, which can be used by the rest of the testers. So for that reason, the MSPC, the mixed signal pin card, is in charge of the clock for the entire 64 pins or 128 pins or 256 pins or 512 pins of digital and analog. Okay, here's how we do it. We have the system clock come in, and then we take it into what they call the analog PLL. It's not an analog PLL, it's a digital phase lock loop, but it's called analog because it goes to the analog components, the MSPC's analog parts, the AWI and the ACI and the modulator and so on. Here's how it works. So we go in and we have a mux for each one of the clocks to go to the clock generator for slot 1A, 1B, 2A, 2B, 3A, 3B, and 4A and 4B. And so those clocks go to the instruments in the instrument slots, which on the MSPC board, the upper ones are clocks 1A, 1B, 2A, and 2B, and the lower slots are clocks 3A, 3B, 4A, and 4B. Each clock generator can generate from 1 to 4.295 billion clocks, that is 2 to the 32. Each clock is an integer division of the selected master clock, which would be the system clock or the system clock via the analog PLL. Programmable from 97.7 kilohertz to 100 megahertz. Each clock can be started or stopped from the CPU or a pattern trigger. We have the system clock and the analog PLL. We choose one or the other. And then that goes to an AND gate where we have a trigger delay. So the clock is started based on the trigger delay from either the CPU start or from a vector trigger where we can start the clock. That goes to a clock divider, which is 17 bits. And then we have our active pulse or the divided clock, and then that goes out to the instrument. We have a pulse counter, which can be 16 or 32 bits, and basically we're counting how many clocks we're going to generate. Those clocks, that's N. That's where you define N, the number of samples you're going to capture, or the number of samples you're going to generate if you're using the AWI. So that's N. So you can capture up to 4.297 billion samples. But you don't have that much memory. But you know, we thought maybe you could upgrade memory. We could go for more memory later on. It didn't really go anywhere, and I'll tell you why in a minute. That pulse counter counts the clocks that you generate, and then after you generate N clocks, it stops the clock divider, so it shuts it down. Or you can stop it from the CPU stops. You can stop the ACI or the AWI from generating clocks. Or you can use vector trigger memory, and so you can trigger it from the vectors. And the vectors are the digital pattern. So the digital pattern, this is mixed signal. The digital pattern is running concurrently with the mixed signal, the AWI and the ACI. And so the digital can start or stop a pattern. And I used to do this for a ramp. I could make a digital ramp. I would generate a bunch of zeros and then generate 1, 2, 3, 4, 5 in digital data. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, and so on, all the way up to 255 or whatever we needed to do for a DAC or whatever. And then I would get to 1, 1, 1, 1, 1 and hold it for several cycles and then stop it. So now I've got 0 to 1, 1, 1, 1, and I can start the capture and stop the capture wherever I want. And I do that in the pattern. So the pattern determines what's going to the DAC, for example. And so that determines what's coming out of the DAC, analog-wise. And so we can start and stop our capture at any point with a delay so we can slew it one way or another, get it away from the problems. Here's a triggering example. %% MSPCDF 4 ACI trigger equals ID ACI1 sample. Pattern trigger pat MAV2 logic single. And we say VEC X0 PS1 timing set 1. The timing set chooses the digital timing for that particular vector. So we have a bunch of vectors, and then we say MSPC start ACI trig, and that starts the ACI, and then we drop into maybe a loop. Maybe that's a label, so maybe we're going to loop around and repeat that vector multiple times. So that's how you trigger stuff in the vectors. So ones and zeros, your truth table data for the digital part, it's all in the pattern. And so then you can start or stop capturing or generating from inside the vectors. Now, why would you do that? Well, here's an example. And I talked about this in another video, a couple of videos. We found on a Philips microcontroller, we had a big glitch. And this is the real glitch. We found we had a big glitch in the waveform coming out of the DAC, because it's a microcontroller that has a DAC and ADC. The DAC would generate a big glitch when we went from 3F to 4.0, because there was some problems with the way the logic is done. And Kamal Pati, the guy who was in charge of testing these things, he was so surprised that we saw that. And he's like, you're not going to show that to anybody else and tell them that we did it, right? You're not going to tell them that Philips did that. Well, if you don't want us to, we won't. So we got his permission to use this graphic without saying Philips. Well, Philips is gone now. Okay, so that's a problem, right? The DAC is working properly. It's just there's a big glitch in the transition from 3F to 4.0. So the DAC is working properly. So what do we do about it? Well, we trigger it at a different place. And so here's what we do. We just trigger it at a different place. And this is a good start. It's not the way to solve the problem, but we can trigger it at any vector we want. So we trigger it one vector later, and we're not at the peak of the glitch, so it doesn't look as bad. So we simply move it over. So we can move it by one T0, one cycle, or we can move it a little bit with a delay. And that's how you do it. That you fine-tune it so that it works the right way. Now, this was all set up to work great. Everybody put a lot into it. Nextest put millions of dollars into this. And then we did True Test. At True Test, they wanted to test 802.11b Wi-Fi transmitter and receiver. And so they were doing DACs and ADCs. I think it was 10-bit DACs and 10-bit ADCs. And we had 14-bit instruments, so it would work great for us. And it was all within our realm, frequency-wise and everything else. And here's what killed us. It was important that you choose the timing generator mode. So timing generator mode considerations. The mixed signal instruments may only be used with the digital in timing generator mode 2. Use the function TG mode to select mode 2, TG mode 2. This is required to ensure proper calculation of the timing generator values when based on the MSPC clock, which may not always be 10 nanoseconds resolution. Well, that was the theory. Remember that on the APG they had a 100 megahertz clock which has a 10 nanosecond resolution. The PLL on the MSPC may change it to something else. So, like on True Test, we changed it to be an 80 megahertz clock. So instead of using 100 megahertz, we use 80 megahertz. So the timing is different for that. So we set TG mode 2. Noel set TG mode 2. We made sure he did. He set TG mode 2, and suddenly nothing worked. He had coded digital patterns. They stopped working. Everything stopped working. And he didn't really look into it. You know, he wasn't the brightest bulb on the planet, honest to God. Nice enough guy, but he wouldn't listen to me. He wouldn't let me get in there and figure out what was going on. So, in fact, the only way I figured this out was I had to wait for him. He was in Taiwan working on this problem for True Test. He told me he's going to have to go back to the Philippines to help his wife or his whatever, his kids or whatever. So he was away from home for like nearly a year. So he had to go home to work out something with his wife or something. And so when he did that, I booked a flight to Taiwan for a week. And so I went there and I found out that there was something wrong. There was something seriously wrong with the timing. So I went in there and fixed it a little bit. I was able to make it work. And they're like, you can make this work, right? You didn't sell us a bill of goods. Well, apparently I did. Because what had happened is TG Mode 2, they told us TG Mode 2, the Nextest people, TG Mode 2 would solve these problems. Well, it didn't. They didn't change the internal structure of the timing generators for TG Mode 2 the way they said they would. And so it relied on the clock being 10 nanoseconds all the time. So it calculated everything relative to a 10 nanosecond clock. So that means that each 64-pin slice was using 10 nanoseconds even though the clock wasn't 10 nanoseconds, and the timing was different from slice to slice, and so it really screwed up the timing. The timing was so bad, all the edges were apart by up to 5 nanoseconds. And so that really killed us on 802.11b, which was pretty fast, 80 megahertz sample rate. That was really fast. So that 5 nanoseconds, that just killed us. So we got horrible numbers. And Noel kept seeing these terrible signal noise ratio numbers. Too much noise, he said. It wasn't noise, they were harmonics. They were harmonics because he had screwed up and not looked at it. What was happening was the edges were all over the place, and so when you do a ramp, for example, or a sine wave with the edges on the timing generator all screwed up, you don't get a sine wave, you get some horribly glitchy thing, and it's harmonics. So we're getting these horrible numbers, and we turned out we didn't know what it was. It took us 2 years to figure it out. Daver finally found it, and it had destroyed everything we did. So nobody in Taiwan would ever buy a Nextest. Nobody in the world would buy a Nextest because we totally screwed up. And the Nextest people, they tried to blame me, but it turned out in the end it was them. The digital people screwed this up. So that's it. That's why we don't have an MSPC. That's why Teradyne, who bought Nextest, had nothing to do with it. They wouldn't even talk about Nextest because it was a complete failure. So everything we did was wasted. All the millions of dollars Nextest spent on us was wasted. So, yeah, it's sour grapes. Okay. I guess somebody's going by. Oh yeah, forgot. So, it was a lot of work. We put a lot into it. I learned a lot. I learned a ton. But it wasn't worth it. We destroyed the reputation of Nextest. It's okay. It worked out okay because we still sold Nextest to Teradyne for $15 a share. So I made a lot of money, over $100,000. And it was wonderful that way. But it could have been so much more. We could have been multi-millionaires. It turns out the guy that screwed this up, he got $6 million from his stock options. So I did everything right. I got a little over $100,000. He fucked it up, and he got $6 million. So that'll tell you, you know, that's the way things work. You got to keep your eyes open. Anyway, so I think that's pretty much it for the Nextest MSPC card. It was a really educational experience for me, but I had to get, after that I had to get out of there, and I went to work for Maxim after that. And even though the CEO called me and begged me to stay, but I wasn't going to stay. But they still took me out to nice dinner with everybody on the table. They must have spent $1,000 on the dinner, so that was great, but didn't make up for what they did to me. They ruined my reputation in Taiwan. Anyway, so once again from the river, this is Dan Bullard. See ya.